Dear students, we have done the revision, and now let us come to the last point that we have studied yesterday. We have seen that we can prepare the alcohol by the reduction of the carboxylic acids and esters. Carboxylic acids are reduced to the primary alcohol in the excellent yield by lithium aluminium hydride, which is a strong reducing agent. So you can see that RCOOH, LiAlH4, and in the presence of water, we can get from carboxylic acid, we can get alcohol RCH2OH. Now, if we take acetic acid and allow it to be reduced into the aqueous medium with the help of the lithium aluminum hydride, we get ethanol. We have a very important reason to study, my dear students, that give reason lithium aluminum hydride is used to prepare special chemicals only commercially. So lithium aluminum hydride is used for the preparation of special chemicals only. Commercially, alcohols are prepared from acids, are prepared by converting acids into first esters and then followed by the reduction. So generally, when we want to prepare commercially alcohols, we prepare from the acid, and first what we do, we convert acid into the esters and then we reduce those esters to the alcohol. So let us understand the reason. The reason is lithium aluminum hydride is a very expensive reagent, and therefore lithium aluminum hydride is used for preparing special chemicals only. Commercially, acids are reduced to the alcohol by converting them to the esters, followed by the reduction using the hydrogen in the presence of the catalyst. So it is nothing but the reduction of ester is done by the catalytic hydrogenation. So you can see that first we should take alcohol, then we allow it to react, sorry, first we should take acid, then we allow it to react with the alcohol in the presence of H plus so that we can get esters, and then ester is reduced by the hydrogen and catalyst into the alcohols. So here, whatever the alcohol we have taken, we get it back. At the same time, we can get the another alcohol. That means this acid is also converted into alcohol. Let us have a look at that. If we have ethanoic acid and ethanol in the presence of H plus, we convert it into the ethyl ethanoate, CH3, CH2, COOCH3, and then with the help of the palladium and hydrogen, we can get two molecules of ethanol. At the same time, my dear students, when we take ethanoic acid and propanol, we allow them to react with each other so that we can get propyl ethanoate, and then with the help of the propyl ethanoate we get propanol and ethanol. So this is how, my dear students, we get the various products. We get various products. Now we shall move to the next one. Let us study it from the Grignard reagent. So this is how, my dear students, the esters are formed from the alcohols. Now we should study about the Grignard reagents. Alcohols are produced by the reaction of the Grignard reagent. Alcohols are produced by the reaction of Grignard reagent with aldehydes and ketones. The first step of reaction is the nucleophilic addition of Grignard reagent to carbonyl group to form an adduct. Hydrolysis of the adduct yields on alcohol. If we take, the first step of the reaction for the preparation of alcohol from the Grignard reagent is the nucleophilic addition reaction. So by the nucleophilic addition reaction, carbonyl compound is converted to alcohol with the help of the Grignard reagent. You can see here the reaction, my dear students. You can easily see the reaction. Let's have a look to this reaction particularly. So what happens that you can see here easily that you first take aldehyde or ketone, that is the carbonyl compound. You have Grignard reagent RMgX. They both combine to give an additive product. This is what it is known as adduct. Adduct means additive product. And then with the help of water, my dear students, we can convert them into the alcohol and MgOHX. So this is the general process. Now let us study the same with few examples. Let us look at the examples, my dear students. Reaction of Grignard reagent with methanol product of primary alcohol with other aldehyde secondary alcohol is produced, and with ketones tertiary alcohols are produced. Please remember, my dear students, that when we have methanol, we get primary alcohol. When we have other aldehydes, we get secondary alcohol. And with ketone, we get tertiary alcohol. So let us study the reaction of RMgX, our Grignard reagent, with methanol. When RMgX Grignard reagent is allowed to react with methanol, we first get RCH2OMgX. In the presence of water, we get RCH2. This R, then CH2OH and MgOHX. So this water is completely added to the RCH2OMgX. Same way, my dear students, if we take any other aldehyde, RCH2, RCHO, and then if we add R dash MgX, then we get R in CH, R dash R, CHOH, that is your secondary alcohol, and MgOHX. Same way, my dear students, if you take ketone, RCOR, and if you allow it to react with R dash MgX, we get RCR, R dash bond OMgX, and that is what it ultimately gives us the water, RCR, R dash OH plus MgOHX. That is what it is, the tertiary alcohol we get, my dear students. So this is how, my dear students, we get the various products. Ethanol, methyl, magnesium bromide. So first we take ethanol, then we allow it to react with the magnesium bromide. In that case, what happens? We get CH3, CH, CH3, O, MgBr. And when we add water, we get CH3, CH, CH3, OH. That is your 2-propanol and magnesium hydroxide, magnesium MgOHBr. So my dear students, this is a very simple reaction to understand. Let us move forward and understand few other examples. You can see here we have taken a ketone CH3COCH3, that is your acetone. We allow it to react with methyl magnesium bromide CH3MgBr. You can see that adduct is obtained. See, this is CH3CCH3. CH3CCH3, this is O of acetone. This O combines with the MgBr, and this C combined with the CH3, and then with the help of hydrolysis, when we add water, we get 2-methyl-2-propanol and MgOHBr. So this is how, my dear students, you can see that this is here OH is bonded to the carbon, that carbon is bonded to 1, 2 and 3 other carbon, and that is why this is the tertiary alcohol that we get here, my dear students. This is nothing but your tertiary alcohol. This alcohol is a tertiary alcohol. And as this is a tertiary alcohol, we can easily understand that whenever there is a ketone, my dear students, from ketone we get the tertiary alcohol. Now next, give the structures and IUPAC names of the product expected from the following reaction. Now, my dear students, we are going to solve some of the in-text questions. Catalytic reduction of butanol. So you can take butanol, 1, 2, 3, 4 carbon, CHO, that is butanol. You allow it to react with the hydrogen in the presence of palladium catalyst. You get butane 1-ol, CH3, CH2, CH2, CH2OH. Then we have the hydration of propene in the presence of dilute sulfuric acid. This is what it is called, the acid catalyzed hydration. So in propene, when we do the acid catalyzed hydration, we get propane 2-ol. Remember, with the help of the acid catalyzed hydration, we get Markovnikov products. On hydroboration, we get anti-Markovnikov products. So this is how, my dear students, we understand the various concepts related to our topic. Now we have the question number C, reaction of propanol with the methyl magnesium bromide followed by the hydrolysis. We have just seen this reaction that we have propanol, CH3C, double bond O, CH3. We allow it to react with CH3 MgBr. The CH3 part of Grignard reagent combined with the carbon directly, MgBr combined with the oxygen. You can see here the additive product or adduct, and then by the hydrolysis we get 2-methyl-2-propanol, which is the tertiary alcohol. Thus, by the reaction of a Grignard reagent with acetone or ketone, we get the tertiary alcohol. Now, my dear students, we want to understand the reaction for the preparation of phenol. So, how can we prepare various phenols? That is what, my dear students, we want to understand. To understand this reaction, my dear students, let us have a look to the various reaction at a time. So you can see here on the screen, you have the various reactions taking place for the preparation of phenol at a time I have shown you. So there are various reactions that takes place, or that is what we can use for the preparation of phenol. The first process that we want to study is known as the Dow process. In this process, we use chlorobenzene as the major reactant and we convert chlorobenzene into phenol. This chlorobenzene is converted into phenol by the reaction of chlorobenzene with the sodium hydroxide at 623 Kelvin temperature and 300 atmospheric pressure. We get sodium phenoxide, and this sodium phenoxide, when reacts with HCl or any other acid H+, it gives us phenol. Now, my dear students, we have written here diphenyl ether. So why do we need to write diphenyl ether here? That is even an interesting case. Let us try to understand. Out of why do we need to add diphenyl ether in this Dow process? So you can see here that just have a look to this reaction. You can see one reaction, that chlorobenzene which reacts with sodium phenoxide. You can see here in the Dow process we have chlorobenzene, sodium phenoxide is also produced. So this chlorobenzene, when reacts with the sodium phenoxide, my dear students, chlorobenzene when reacts with sodium phenoxide, it produces diphenyl ether. Now, when diphenyl ether is formed, it is an unnecessary product. We actually want to prepare phenol and we get product as a diphenyl ether. So to reduce the preparation of diphenyl ether, initially from the beginning itself, if we add diphenyl ether, the equilibrium of preparation of diphenyl ether will move towards the left side and we will have more chlorobenzene available for the production of phenol, and that is how we get better yield or better product. And that is why, my dear students, during the Dow process, you can see here I have written diphenyl ether, which is not mentioned in your textbook, but it is very important to understand that during the process of conversion of chlorobenzene to phenol, it is necessary that diphenyl ether is added from the beginning so that we can get a better product of phenol. The next process for the preparation of phenol, my dear students, we are going to study is known as the cumene process. You can see here I have mentioned here the next process. The name of the next process is nothing but your cumene process. So let us study cumene process, my dear students. You can see here cumene. This is your compound known as cumene. Cumene is actually produced from benzene. So you can see benzene, it is allowed to react with the propene in the presence of H3PO4 phosphoric acid at some elevated temperatures, it gives us cumene. This cumene is allowed to react with the oxygen present in the air so that we can get cumene hydroperoxide. This cumene, when it is allowed to react with the oxygen in the air so that we can get cumene hydroperoxide. This cumene hydroperoxide, when it is hydrolyzed in the presence of H plus, it gives us phenol. At the same time, it also gives us acetone. You can see here, my dear students, I have clearly mentioned that the acetone is the byproduct for this particular reaction, which is known as the cumene process. So, dear students, a very important questions that we are going to face or we are going to study here is this question. Let me read the question for you. Out of cumene process and Dow process, which one is preferred and why? Out of cumene process and Dow process, which one is preferred for the preparation of phenol and why the process which we prefer is preferred? So let us have a look to this. Out of cumene process and Dow process, cumene process is preferred because it gives better yield and acetone as a byproduct, which is very useful product. In Dow process, chlorobenzene reacts with sodium phenoxide to give diphenyl ether that reduces the yield. Reduces yield means it reduces less yield is produced. And that is why initially we need to add diphenyl ether in the Dow process. So to get better yield, diphenyl ether is added during the Dow process. According to the Le-Chatelier's principle, the equilibrium moves towards the chlorobenzene and more chlorobenzene is available for the for the process of preparation of phenol, and that is how Dow process is less preferred and cumene process is more preferred because during the cumene process more amount of product is being formed. Now, my dear students, we are going to study the preparation of phenol from benzene. You can see here the reactant that we have taken is benzene. Benzene is allowed to react with oleum, that is H2H2O7. Here the process of sulfonation takes place. Remember, this oleum is also known as the fuming sulfuric acid. That is your H2H2O7. So we get benzene sulfonic acid. This benzene sulfonic acid, when allowed to react with sodium hydroxide alkali followed by the acid, we get phenol. So this is even a very important reaction for the preparation of phenol by using benzene. So you may be asked to convert benzene into phenol. You can use the sulfonation followed by reaction with alkali and acid. We get phenol. Now the last reaction that we want to study is known as the reaction, that is the preparation of phenol from aniline. We are going to revise it 3 or 4th time, my dear students. We know that when aniline is allowed to react with sodium nitrate and HCl at 0 to 5 degree centigrade temperature, diazotization takes place. So due to diazotization, we get benzene diazonium chloride. This benzene diazonium chloride, when it is warmed with water, we get phenol. So again, we can use the reaction called diazotization, so that by the reaction of diazotization, we get benzene diazonium chloride, and benzene diazonium chloride, when treated with warm water, it gives us the phenol. So these are the various methods of preparation of phenol, my dear students. My dear students, if you have any doubt, you can ask me. Have you understood everything? Do you want to ask me something?
Yes.
If you want to ask me something, ask. or shall we move to the next portion? बच्चों आपको कुछ पूछना है तो पूछ लीजिए, वरना हम आगे चलते हैं। नहीं पूछना तो बोल तो दीजिए कि नहीं पूछना है।
नो सर।
ओके,
No, sir.
No, sir.
चलिए बच्चों, then let us solve some other questions. Question: show how are the following alcohols prepared by the reaction of suitable Grignard reagent on methanol. So first we want to prepare CH3, CH, CH3, CH2OH. This we want to prepare using the methanol. So with methanol we will allow it to react the Grignard reagent. The Grignard reagent would be isopropyl magnesium bromide. This isopropyl magnesium bromide, when combined with the Grignard reagent, you can see the adduct is formed, and this adduct finally gives us the desired product, which is given into the question. Now we can move to the next one, my dear students. We want to find out the 1-cyclohexyl ethanol. So to get the 1-cyclohexyl ethanol, we first take methanol and allow it to react with the cyclohexyl magnesium bromide, and finally we get 1-cyclohexyl methanol. Write the structures and product of the following reaction. You can see CH3 bond CH double bond CH2. This is 1-propene. When it is acid catalyzed, it gives us 2-propanol. You can see here we use a reactant where we use NaBH4. It is a strong reducing agent. Though it is a strong reducing agent, it does not affect the ketone of the side chain, but it affects the ketone present on the cyclohexyl ring only, and it converts ketones into the alcohol. Same way, my dear students, here it is an aldehyde. This aldehyde group is converted into alcohol with the help of NaBH4. So now, my dear students, we are going to study some of the important physical properties of alcohols and phenols. Alcohols and phenol consist of two parts. One is alkyl or aryl part, and the another is hydroxyl group. The properties of alcohols and phenols are chiefly due to the hydroxyl group. The nature of alkyl and aryl groups simply modified these properties. The nature of alkyl and aryl group simply modified these properties. So let us understand the first property, that is what it is known as the boiling points. The boiling point of alcohol and phenol increase with increase in the number of carbon atoms, increase in van der Waals forces. So as the number of carbon atom increases, van der Waals forces also increases. In alcohols, the boiling point decreases with the increase in carbon chain. Because of decrease in van der Waals forces with decrease in surface area. As the surface area decreases, the van der Waals forces also decreases. So in alcohol, boiling point decreases with increase in carbon chain. Please remember this, my dear students, that as the carbon chain increases, the boiling point. So, my dear students, as the branch increases, my dear students, as the branching increases, due to increase in the branching, the surface area decreases, and as the surface area decreases, the van der Waals forces decreases. So if you have 7 carbons and all the 7 carbons are available in a single line, or they make the branches, then the branching one, the alcohol with the more branches will have lower boiling point as compared to the normal alcohol where all the carbons are present into the single line. The OH group in alcohol and phenol is involved in the intermolecular hydrogen bonding as shown below. You can see that we have ROH, then we have HOR, then we have OHOR. So all these alcohols, they have hydrogen bonding. You can easily understand. This is alcohol. This is even your alcohol. You can see that all these alcohols, they have hydrogen bonding in between them. So these alcohols, when they are connected with the hydrogen bonding, you can see that they have hydrogen bonding and their boiling and boiling point are being increased. Same way you can see with the red dots, I have shown you the hydrogen bonding among the phenols. The same thing is shown here. There is a hydrogen bonding among the alcohols as well as phenols. So boiling points of alcohols and phenols are higher as compared to the hydrocarbon, ethers, haloalkanes and haloarenes of comparable masses, or we can say the comparable molecular masses. Let us study the same by one question. Arrange ethanol, propane and methoxymethane in the increasing order of boiling point. So we have propane is less than methoxymethane is less than ethanol. That means ethanol will have the highest boiling point as compared to the ether and hydrocarbon. You can see that the hydrocarbon has got 23 Kelvin, 231 Kelvin, ether has got 248 Kelvin, whereas alcohol has got 351 Kelvin boiling point. This is what it is possible due to the presence of the hydrogen bonding among the alcohols and phenols. The high boiling point of alcohols are mainly due to the presence of intermolecular hydrogen bonding in them, which is lacking in ethers and hydrocarbon. So ethers and hydrocarbon have lower boiling point because they do not have hydrogen bonding, whereas alcohols have hydrogen bonding and that is why they have higher boiling points. Now, my dear students, we have the next topic to study is about the solubility of alcohols and phenols. Solubility of alcohols and phenol in water is due to their ability to form hydrogen bond with water molecule as shown above. You can see here, my dear students, this is our alcohol molecule. This alcohol molecule is bonded with the water molecules. You can see these are the various water molecules. I can show you. This is water molecule. This is even a water molecule. You can see here this. You can even see this another water molecule. These all water molecules are bonded to the alcohol. Two water molecules are bonded with the oxygen of alcohol, whereas one water molecule is bonded with the hydrogen of the alcohol. So you can easily see here, the solubility decreases with increase in the size of the alkyl or aryl group, that is hydrophobic group. You can see, my dear students, that this part of alcohol is hydrophilic, but this part of alcohol is hydrophobic. This is hydrophobic part. As this is the hydrophobic part, my dear students, as this part is hydrophobic, this hydrophobic part, so as the number of carbon increases, we get more and more, or we get the solubility of alcohol decreased into the water. Several of the lower molecular mass alcohols are miscible with water in all proportions. So methanol and ethanol are the kind of alcohols. They are miscible in water in all proportions. Next question. Arrange the following set of compounds in order of their increasing boiling point. So pentane 1-ol, butane 1-ol, butane 2-ol, ethanol, pentane 1-ol and methanol. So let us arrange them. Let us answer this question. So increasing order of boiling point is methanol is less than ethanol, is less than propanol, is less than butane 2-ol, is less than butane 1-ol, is less than pentane 1. So my dear students, as the number of carbon increases, the boiling point increases. So the lowest boiling point is 1 carbon, then 2 carbon, then 3 carbon, then two compound of 4 carbon and 5 carbon. Now among these two compound of 4 carbon, butane 2-ol is branched and butane 1-ol is linear. So we have just seen that when there are branches, there are less van der Waals forces, and as there are less van der Waals forces, the boiling points are or melting point are lesser, and that is why the branched 2-butanol has lower boiling point than normal or linear butane 1-ol. Same way we have the another question to solve: normal butane, ethoxyethane, pentanol and pentanol. So we can easily arrange them as normal butane is less than ethoxyethane is less than pentanol is less than pentanol. You can even remember this, my dear students, that if the number of carbon are same, hydrocarbon will have lower boiling point than ether would have lower boiling point than aldehyde would have lower boiling point than the alcohol.